we have finished talking about quantum postulates. In other words, if we look at quantum computing, we have finished the quantum part of it. Whatever, or I would say mostly, whatever we needed from quantum mechanics, we have formalized them as postulates, and this has given us a structure to work on. This tells us how a quantum system works. Now, for some small time, we'll talk about computing. What would we need from computing? If you talk about classical case, most of the time, computation is formalized in terms of Turing machines. I would assume that you are familiar with Turing machines, asymptotic notation used in computer science. This is like theta 1, order of 1, omega 1, notations like that. Otherwise, you can look at the book by Arora and Barak, or you can also look at the third chapter of Nielsen and John, our standard reference. That way you will be updated with these notions. You just need to know their importance in classical computational theory. You don't have to worry about going into details of all these concepts. And if you know about Turing machine, then you know that by weak Church-Turing hypothesis or strong Church-Turing hypothesis, we define what computation is using Turing machine. Anything we can do by a Turing machine is called computation, or whatever we can compute, we are able to do it using Turing machine. Strong Church-Turing hypothesis says that if we can compute efficiently on any model, then we can compute it efficiently on Turing machine. In other words, if we have to say what we can or we cannot do, we have to just say whether we can do the same thing on a Turing machine. Now, we know what a classical Turing machine. Going to quantum computing, a question emerges, what about quantum Turing machine? Deutsch in 1980s defined the concept of quantum Turing machine, but then most of the time people talk about circuit model instead. Instead of talking about Turing machine, they talk about something called a circuit model. It turns out classically and quantumly that Turing machine model is equivalent to circuit model. Though this equivalence, I should put it in quotes because it requires some clarification, and this is our job for today. Our first job is to understand what classical circuits are, and second job is to understand this equivalence. Under what condition Turing machine can be said to be equivalent to circuit model. And we will do all this in the classical framework first. Then in the next video, we will talk about quantum circuits. So let's talk about classical circuits. What are classical circuits? You must have seen classical circuits made with AND or NOT gates before. Generally, they are drawn differently, but for the sake of simplicity, I will just write them as gate. This is saying that I have 2 bits as input, x1, x2, and AND gate is applied to it. The output will be given on this new wire. Similarly, I have made 2 copies of x2, AND gate applied on x2, x3, and then output. I have three AND gates in the beginning. This is a copy of x1, this is a copy of x3, and then all these three outputs are fed into an OR gate, and this is the output of the circuit. This is one way to draw a circuit. You might have seen top to bottom representation of this circuit. Don't worry, it's the same. Here, this is left to right representation. Both of them are equivalent. We will mostly talk about left to right representation. This is a circuit, and we remember here that no wires go from right to left. The circuit proceeds from left to right. In that sense, we feed input x1, x2, x2, x3 in these AND gates, then the output comes out, then it goes to the OR, and then we get the output of the circuit. That's how we understand the circuit. And the reason behind this is that in case if we have two gates, G1 and G2, such that output of G1 goes to input of G2 and the output of G2 goes to input of G1, this will lead to conflicting values. This should not be allowed. If you know this terminology, then we say that circuit is a directed acyclic graph. If you don't know this terminology, then just remember no wires from right to left. This also means no cycles in the circuit. This avoids these conflicting values or confusion, and we know how circuit proceeds. Though it can happen that one output can go to multiple gates. We already saw in the previous case that there were two copies of x2. Even after we get an output, even that can be copied. This is called a fan-out gate. Becomes like this, and then one can be fed into OR gate, one can be fed into XOR gate, or whatever you want to do. In other words, one output or bit can be copied. This is called the fan-out gate. I will point out that this is not possible in case of classical quantum circuits. The reason being, copying is not a unitary operation. You remember that anything we can apply in a quantum circuit has to be unitary. It turns out that copying is not a unitary operation. That means no quantum fan-out gate. Though in classical circuits, we can have this possibility. There is a small difference between fan-out gate and extra wires, or in quantum, what we call registers. These are the lines I am drawing. This fan-out gate is not allowed in quantum, but extra wires are allowed. This is like temporary variables or extra workspace for your algorithms in a classical circuit. Your input might be x1, x2, x3, but then you might have some extra work registers, and you can have gates, and then you can say, okay, this is my output of the circuit. That is completely fine. These extra workspace bits are called ancilla bits or qubits. these are allowed in quantum circuits. I should remind you about this in quantum case, but it is important that in the end they should not be entangled with the output. Otherwise, they can affect the outcome of the output. Generally, we take these, and in the end, we as either if they are entangled, we measure both and then make sense of statistics, or they are unentangled with the output and then we measure output. This is something to be this. No, I'm not saying this is wrong, but what I'm saying is that this can affect the statistics. If the ancilla is entangled with the output, it can affect our statistics, and we have to take care of that. But they are allowed. Ancillas are allowed to exist in quantum circuits. This looks like a quantum classical circuit which has Fanout gates, extra workspace, and or NOT gates. A natural question could be, what gates are allowed? Or actually, a question could be, what is a gate? Let me answer that first, and then we can talk about what gates are allowed. For us, a gate is a function which takes some number of bits and gives an output. Mostly for a gate, there will be one output, but for general sake, we can say that it can have multiple outputs. This is what a gate would be. It has k bits as input and L bits as output. Basically, it is a Boolean function. Calling this a gate, then we again ask the questions or a question, what gates are allowed in a circuit? Your natural instinct might be all gates, but that clearly is wrong. First, we can't assume a computer which has access to all gates. Second, if all gates are permissible, then we can compute all functions. A circuit computes a function, and if we are allowing all gates, then we can just put that, whatever you want to compute, we can put that as a gate and we can compute it. So this is a meaningless notion of a circuit when we say that all gates are allowed. In general, when you have seen circuits, we talk about AND, OR, NOT, and NAND, XOR gates. These are the gates which we can construct. Then it makes sense to say that our computer has access to them, and then we say that only certain gates are allowed. These certain gates come from some set. If this family of set is very small, then it is not that useful. We generally assume that we have a universal gate set. That means any function can be computed using these gates, though it might take a long time. This is the essential question of circuit complexity. We know all functions can be computed. One such universal gate set is AND or NOT. another is NAND, and here if you give enough time or if you give enough AND or NOT gates, then I can compute any function. This follows by looking at the truth table. The fact that is we can compute any function using AND or NOT gates just on 2 bits. So AND and OR will be on 2 bits, NOT is a 1-bit function. This allows us to compute any function, but the question in complexity is, can you do it fast? Can you use less number of gates? In other words, a function is easy if it requires less number of universal gate sets. Or I should say gates from a universal, gates from the universal family. Less number of gates from a universal gate set. And similarly, a function is hard if it requires lot of gates from a universal family. We define what universal families are allowed. Sometimes we take them to be NOT or AND. Sometimes we take it to be NAND. And conversions between these things are known, but essentially what we have to take away from this discussion is that you will be given a universal family, and whatever you want to compute it using few gates from this family. The few notion will be clear from the context. It might be polynomial in time. You already know the asymptotic notation. So sometimes you want to linear number of gates, sometimes you want polynomial number of gates, and all that will be clear from the context. But essentially, this is the problem of circuit theory. You are given functions and you want to compute them with as less number of gates as possible. We know now what circuits mean for us, and as I said, the next part will discuss how they are equivalent to the Turing machine model. This notion which allows them to be equivalent is called uniformity. We will talk about uniformity now. Remember, this notion is introduced so that we can talk about equivalence between Turing machine and circuit model. Let us start with a basic question. Can we directly say that whatever a Turing machine computes, a circuit can compute the same thing? Someone who is more attentive will notice that that cannot be true. Why? Because Turing machines compute languages which are subset of 0, 1 star. On the other hand, we just now saw that circuits compute functions where we have a fixed input size. We don't have to worry about L because if there are more outputs, we can think of computing multiple functions. And let's now restrict our function to be just have 1-bit output. Turing machines are computing languages. There is no fixed input length. In circuits, we do have that. They cannot be equivalent. What is the fix? A small fix would be Turing machines what will be equivalent to circuits, not just one circuit, but a circuit family. Let's say Cn, where n goes from 1 to infinity. N denotes the input length. In other words, whatever Turing machine can compute, we can compute it using a family of circuits where we will give one circuit for each input length. This might seem like a reasonable notion. And then we might want to say that whatever a Turing machine can compute, it can also be computed using a circuit family. Unfortunately, this notion of a circuit family turns out to be very strong. In other words, it can compute an undecidable language. If you are not familiar with this, don't worry about it. Just notice that it will compute something very, very strong. Undecidable are languages which cannot be computed by a Turing machine. And why is that? Let's look at the set S. It is going to have one string for each length. And a particular string S, element of S, will be such that Si is 1 if and only if ith Turing machine halts. Here we can give an ordering to Turing machine. That's not important. Once we give any particular ordering, we can define what it means by ith Turing machine. So if I have a string of size 2, it will just say that whether the first Turing machine halts and whether the second Turing machine halts. Now you can easily see that since I can't solve halting problem, this language is undecidable. This is too hard for any Turing machine. This will follow by a diagonalization argument. But on the other hand, notice that there is only one string of each length by construction. And that can essentially be hard-coded in a circuit. Since we are allowed to have circuits of every length, two circuits of different length need not be similar in any sense. Then we will look at the string, which is the correct output for that length, and we will just hard code it in a circuit. We will make a circuit where only that input will be accepted and nothing else. That's easy. You can just make it using AND or NOT gates, and then this is showing that our circuit family can compute it. This notion turns out to be too strong, essentially because we are allowing the different circuits of different length, to be completely unrelated to each other. And that's where the criteria of uniformity comes in. It intuitively wants to say all circuits of different length should be identical. I shouldn't say identical, but should be similar. Now the formal notion for this going to be that a Turing machine given n can compute Cn efficiently. So this is going to be a very, very complicated notion. We will just assume that this will follow if we give intuitively similar circuits, where our circuits are not designed by keeping length in mind. And this will be clear to you when we take multiple examples. And that would be enough to show that our circuits are uniform. We will not worry about this thing that we will not give a Turing machine which comes up with these circuits, but our circuits will look so much similar for every length that it will be quite clear to us that they are a uniform family. And it turns out that uniform circuit families have same amount of computational power as Turing machines. Quantum circuits work in the same fashion, or when we talk about quantum computing, instead of talking about Turing machines, we talk about quantum circuits. And this is going to be our topic for the next video. Thank you.